So this is our presentation for our project that we've worked on all semester. It's mine detection using neural networks. My name is Megan Ledoux. This is Ricardo Martinez and GROUP1. So our abstract, we set out to design a system that had inputs of return sonar signals. And with those signals, our system will extract particular features. And through comparative computation, it will give us two types of output, whether there is a mine present within our sonar signal, or whether what type of sediment is at the bottom between sand, mud, and sandy mud. So this is our overall method from the VSS, which is our volume sonar system. We're going to take the returns and pass it through a low-pass filter and pre-compute it, the particular features. This is the process that we took in order to feed these particular features that we've processed into the neural network to train the network. Also, something that we're going to pass to the neural network is the graininess feature, is what we call it. It's basically just taking the raw signal and passing it through the neural network as well to kind of, before the noisiness has been smoothed out, we'll note because the graininess is an additional feature that does get lost through the filtering. So we're going to keep that, train the neural network with that feature as well. And in the end, the neural network will output two different types, whether there is a mine present in the particular data and what type of sediment type was at the bottom. For this project, we focused on three particulars: the sand, the mud, and the sandy mud. So for the sonar specifications for the VSS, the volume search sonar, we had two horizontal beams. The sonar contains about 54 beams. It operates at a frequency about 30 kilohertz. And this is just a picture of it. Not that we really saw any of this in real life. So this is the beam configuration. There's two sets of beams, kind of like a forward beam array and a kind of toward the backwards beam. Here's the illustration. The beam 14 is we call it nadir beam. It goes straight down, and the values and the computations coming from this beam would be the most accurate. And so for the contents of this project, we focused mainly on the inner 6 beams because those were the ones that were closer to the ideal data, I guess. Whereas the further out beams, the angle would be greater, and it'd be harder to compute. So these are the ocean bottom characteristics with the sediment type. We have 7 particular classifications: gravel, sand, silt, clay, mud, boulder. These classifications are based on grain size, attenuation, reflectivity, impedance, and that kind of thing. It's like a set classifications. For this project, like I mentioned before, we're going to focus on sand, mud, and sandy mud. And a clear way to identify between these 3 types of sediments is their graininess. So Ricardo's going to take it from here.
Thank you, Megan. As you guys can see, these as she outlined the different beams, this is what our nadir beam looks like. This is the beam that points straight down, and this is a beam that would be further off to the side, beam 1 or beam 23. That, as you saw on that diagram back here, the nadir beam would be this beam straight down, and then these beams would be off to the side. So this would be our nadir beam, and these are our side beams. We focused for this project on the middle 6 beams because, as you can see, there's very little data to be collected from this. Those beams just go off into the water and they don't return until way after the middle 6 beams do. The middle 6 beams actually impact the ocean bottom.
So what y-axis in the return signal plot? Is this over time or
it's
reflection over time?
This is our time series right here, and this is the amplitude of our signal.
Okay.
Is that, I think that's what you're asking.
Yeah.
Okay. Oh, okay. In order to filter, we took this return, which is we can't extract very much information from this other than the graininess feature, which we is going to elaborate on. But we filtered these signals using a 100th order median filter. That was the one that gave us the cleanest result. It's a very high order filter, but we risked losing a lot of information doing that, but we still went with it because we needed to extract certain features. We needed to extract the maximum peak. We needed to extract the slope at that peak, both approaching the peak and leaving the peak. We needed to determine the area under the peak and the standard deviation of the extremes, meaning the standard deviation at the ends of the signal, out here and out here. That would determine our graininess feature. Then we transformed it. This is time series. We transformed it into the Fourier domain, and we determined the phases that are apparent inside the signal. This is what our filtered signals look like after 100th order median filter. These are exactly the same beams as was shown before. This is after they were filtered. This is the clean sonar signal. We would take these signals, these unfiltered signals, and we would run them through this program right here, our MATLAB program. It's fairly lengthy. What it does is it extracts all those features. First, what it does is it filters the signal. Then it extracts all the features with the exception of the graininess. That's already pre-computed. And then we take those features and we store them in a row vector form inside MATLAB. We then take those row vectors and we run them through a neural network which has already been trained. The output of the neural network, as Megan covered before, is supposed to say whether this sonar return contains a mine or no mine, and if a mine or no mine exists, what sediment type is on the bottom. We focused on 3 sediment types: sand, mud, and sandy mud being in between. Just a little background on neural networks. This is essentially how it works. These are your input neurons, which are inactive. They go into, by inactive I mean there's no processing that occurs at these nodes. You just have an input signal. They go to different hidden nodes depending on how many layers that you have. These hidden nodes are where the weighting and the computation and processing takes place. And then, of course, you have your output node. These are the different functions associated with it. I don't try to understand some of this math. Some of this math is fairly high-level fractional Fourier transform stuff. But essentially, this is your weighting function when you use backpropagation, and it transforms your backpropagation signal, your feedback. I do remember that from controls. This is your feedback signal right here. So we actually used a feed-forward network with backpropagation. This is just a feed-forward network picture. There is no backprop in here, but essentially it would look similar to this. I was trying to find a formula that would involve backpropagation in there, but it didn't have it, so I had to include it separately. This is what our neural network looked like. This is what we started out with. We had feed-forward with backprop, as I said. We chose 2 layers with 10 neurons per layer. And we considered using several different networks. We settled on the feed-forward with backprop because it was the simplest network and it was the most reliable. Unfortunately, we didn't have more time to train different types of networks, but there are those that exist out there that may be more optimal. So we haven't had the opportunity to find out if there's more optimal. I'll now turn it over to Hui, which will explain the methodology and everything behind our code.
All right. The first thing to know that to start training our network, we needed to set some sort of target. These targets are basically, these are the mines. If there's a mine, these will be 1s. And if it's a sand, it'll be 1 on the second one. It'll be a 1 for the third one if it's a mud. And lastly, it's going to be mud sand if it's going to be it's going to be mud sand if it's going to be on the 4th one. To do this, we needed to feed into the neural network all these features in a certain order to so that the neural network can recognize what is the differences in each of these characteristics. First, it's going to be the slope, the second slope, which is right after the peak, first slope being before the peak. The standard deviation, which will be computed from the graininess at the slope itself, and finally the maximum. I actually made a mistake and didn't really include the integrals, but it really didn't make a difference in the end. I'll explain later. Afterwards, we're going to use the neural network, and if it's a 1 or close to 1, then that's going to be like our best option, whatever it is. Yeah. And this is basically the input data for our neural network. See, this is going to be our target right over here, and then our input data is going to be somewhere up here. Yeah. Yeah. This is part of slope 1, slope 2, and so on and so forth. This is the neural network. We use the neural network toolbox in MATLAB to do this. We just set a whole mess of features right here, and we have a target. This first feature is comprised of feature 1, feature 2, and feature 3, so that we can test feature 1, feature 2, feature 3 being sand, mud, muddy sand. And the features is just a compilation of all of those. This unknown right here is just a signal that we just don't know what the sediment type is. And we simply just set a target right there. And so this is going to be what it looks like. We have 92 inputs coming in with 2 layers. And then afterwards it's going to go through a transfer function, and then finally it's going to come out with the output. Right here, this is when I started training it. It's supposed to go straight down. Ideally, it's supposed to go down to 0. That's what the goal is. But it's close enough so that, you know, it's relatively simple.
In your class, you have training, validation, and test. Why there's only one curve in this display?
This is only training. Well, I didn't do any validation tests like that. It's just we just set a target so that it can train it to match this certain, say, generality, I guess. These are the results that we got. I trained it twice. This is the first one right over here. As you can see, it's going to be like relatively what we would want. And this is the second one. You can see, I don't think you can see this, but it's 1, there's another 1, there's another 1. These are all zeros around there. Yeah. And so afterwards, I simulated the unknown one as well. And this is what I got. I was really thrilled when I saw this. It had 0, 1, something close to 0, and 0.249. So that means that this signal is going to be a sand sediment, and it's going to be close enough to muddy sand, which is, you know, pretty common. So I was pretty happy about that. I'm glad it wasn't anything high like 0.7. So I think our neural network worked. It's just that we did not test it with any mine signals because we didn't know what it would look like. We didn't know what, you know, characteristics we were supposed to be finding. So, but this is what we got, and I think, yeah.
As Hui mentioned, one of the biggest challenges that we faced on this project was we had no idea what a mine would look like. The Navy doesn't exactly share sonar returns of mines or bays, so we couldn't really find any data to test it under mine conditions. We're confident that it would work because we've trained it without mines. So if you input something, it'll tell you if there's an object there or not. We wouldn't be able to tell you exactly if it was a mine or not. We would be able to tell you the size of the object, we would be able to tell you how deep the object is, so on and so on and so forth. But we wouldn't be able to tell you if it was a mine without exact mine data from the Navy or some other source that has mine data. That was our biggest challenge. But we were able to determine sediment type, which was a big leap. Now all that we needed was mine data to train the network with, and then we're fairly certain that it would function properly. Something else, we had very little familiarity with MATLAB and the neural net toolbox. That was difficult for all 3 of us to overcome, but we finally were able to, thank God. And training the network. Training the network was also a challenge. We had a lot of inputs, and we didn't know exactly how to work it. We'd never taken a class in neural networks before, so it was a big learning experience. As I said earlier, we don't have any mine data, but hypothetically this system would work to detect mines, or at the very least an object at the bottom. If we had mine data, we could train our neural network to recognize that mine data. it functioned as expected, and we met our project goals, which is what we said. We wanted to determine sediment type and if an object existed. So we can determine that. We just can't tell you if it's a mine or not yet. We would like to thank Dr. Bourgeois because she was very patient with us. Unfortunately, she's not here for us to thank her. And Dr. Demetrius for giving us the opportunity to research and for helping us out. We did have some last-minute problems that he helped us out with yesterday. So, any questions? Dean.
You mentioned that you use the middle 6 beams.
Yes, sir.
For your processing.
Yes, sir.
But that would be asymmetric. If the nadir beam is straight down, how do you get 6 as
what we did was
symmetric?
That's actually a correction. I actually used all 23 beams. So
that was my next question. Later on, you said that in MATLAB you use all 23 signals.
Yes.
Yeah,
I made a mistake when I compiled the presentation. I apologize for that. We were originally, Dr. Bourgeois wanted us to focus only on the middle 6 beams, and then we compiled a MATLAB program. It was a simple for loop to make it include all 23 beams that were present. So we ran all 23 beams, but the outermost beams are not going to contain very much data at all because they're very trashy looking.
Why would you have concentrated just on 6, though? If you have one that's straight down,
it's supposed to be
seems
7.
like you'd want 3 on each side.
It's 7.
Seven.
I want 7.
I apologize. It was 7.
It should have been 7.
Should have been 7. You're right.
Okay.
I apologize. You're right. 1 down and then 3 on each side.
Okay.
Back one slide.
This one.
One more. There.
There. Okay.
So this first on the left is the noisy signal, unfiltered,
Yes.
unattenuated, and nothing does.
Both of them are
Straight sonar
unfiltered.
signal
Yes.
Of all 23.
No, this is
just one beam.
this is one beam.
Okay.
This is
and that one's going to be nadir over there.
yes. This is beam 14, which I believe beam 14 was our nadir beam, and then this is either beam 1 or 23. It's one of the extreme beams.
And are these y-axis normalized, or they are just the raw magnitude of the sonar?
This is the raw magnitude, raw data. Nothing has been done to
this
this.
shows that high. I mean, this is like 15,000.
This is 15,000, and this one's 1,000.
Yeah.
The reason these are the returns that we were provided with from Dr. Bourgeois. I estimate that this signal didn't have a high amplitude because it was a signal that was directed out essentially at infinity. So it returned very later on, and it returned much later than this beam did, and it also didn't strike anything. It was out in the middle of the water, and then it came back, if you understand what I'm saying.
Well, but
So it wouldn't have a very large return, whatever it
and
did.
if you have 2 different compounds in the, I mean, in the sea floor, then would this sonar return be seen from the raw data? You cannot see anything, or you can only find some characteristic feature after you do the medium filter?
Well, we can find. Do you want to answer that one?
Yeah,
Okay.
actually, this one's actually the reason why this one's so high is because the reflection is going to be so fast that it doesn't have time to have that separation between the reflection and the ping.
Okay.
This first one right here, this is the ping, and afterwards you can see clearly that this is the reflection afterwards. And your question after that was?
Because you said that you can, essentially you cannot maybe determine whether it's a mine or not, but you know some data for sandy or some other sandy.
Right.
Right.
But from that, do you have, for instance, the raw sonar data for different compounds, because the return from different compounds?
Yes.
Yeah, I think I understand what he's asking. Yes. What we assumed was that sand, since it was grainier, would be further apart, so this signal would be noisier. If it was a boulder, for example, which we didn't test, but if it was a boulder, which would probably be the opposite of sand on the scale, this would not be as noisy or as grainy. There would not be as much of a stick.
The fluctuation would be smaller on either.
Yeah.
Yes, your standard deviation would be more
It's
small.
going to be less fluctuation.
Yes. Did that answer your question, Dr.
Yes,
Chen?
thanks.
Okay. Any other questions?
I have one question. This technique would apply to the mine just under the sea floor, or it can penetrate down to beneath the floor?
That would all depend on the sonar that's being used. The sonar that we actually modeled was the volume search sonar, which is designed to search for objects embedded in the seafloor. So it would work for things which are buried. I don't know how deep it would go because the exact specifications of the sonar are classified, but I estimate anywhere between 1 foot to 3 feet, maybe even deeper.
How
It-
much? I'm sorry.
1 foot to 3 feet, I would estimate. as I said, a lot of the stuff with this project has been classified, like the volume search sonar and things of that nature. So Dr. Bourgeois provided us with some unclassified material because she actually worked on that project. But most of what we were dealing with, we had to simulate or estimate, since no one was willing to give us this classified data.
Ideally, we would really want more data to feed into the neural network so we can get a clearer picture of what, you know, sand, a mine, muddy sand, like things of that nature. And even if that would happen, I would guess we would also want, you know, things like boulder, gravel, and stuff like that. We would also want those sediment types as well.
The system itself is expandable, so all that you have to do is actually acquire this data, train your network, and then you can test for whatever you just trained your network to be able to detect. So it's a very expandable network.
One thing I'm thinking is the mine is always covered by sand or mud.
Right.
So sometimes you may detect sand or mud.
Right.
Cover the mine.
We detect, but right. But ideally, what's going to happen is the graininess. For example, let's say that this was an object, right here. This was an object. It would still have a graininess, but this amplitude would determine the return of that object. So if that object was, say, made of metal, you would get a really nice high spike. It would be grainy, but the amplitude would be there. So what would happen is you would filter it into this, and then you would be able to extract these features. You would also be able to tell what it's buried in. So from basically, we would take the area underneath this peak, the slope approaching this peak, and the amplitude of the peak. Then we would also Fourier transform it and take the phase.
The x-axis is the frequency or the time?
The x-axis is the time series.
Time series.
This is in the time domain.
Thank you.
Any other questions? Okay. Thank you.
Thank you.